Thank you. My name is Peter, as Omar said. I'm a network engineer at Facebook. And the talk is called OpenR, Virtual Packet Routing. So OpenR is the system Omar mentioned, is our own routing solution, what we use in data center, backbone, and other applications. For those who like structure, we'll go over the motivation for this protocol. Design aspects, probably the most in-depth section. Discuss deployments and future plans. Before I start, I would like to extend a huge thank you to the team that made this work possible. All these folks worked really hard to get this project a reality over last year. Most initial question people always have when we present stuff like this is like, why would bother with a new routing solution? I mean, we have lots of routing protocols already. They're pretty mature, stable, like work really well. Like what's wrong with BGP, for example? Like as you know, BGP has been used very successfully in data center in the backbone for years now. There are people who spend lots of efforts making this a standard or something like this. Yet we still bother and try to get something better. And that's very simple. We need to move fast. We need to innovate. And it's really hard when you have something fixed and not controlled by yourself. The main problem with any protocol that you have in the network is that you don't control it. You don't control the source code. You don't control bug fixes. You don't control the features. At Facebook, we really like to innovate and experiment. And having a solution in the network which we don't control was blocking us. So this whole discussion, I think, began in 2014. We started arguing, hey, what should we do to replace BGP, for example? As usual, it just was lots of arguments. Network engineers like to argue a lot about routing. I think we spent like a few weeks just in discussions. And then finally, we sat down, wrote some simple implementation, and thought about this a bit more. What they came to is that we don't want just a routing protocol. Because they already exist, they work pretty well. Instead, we try to create something bigger, a routing platform that allows us to create more applications in the network. And so the basic idea was pretty straightforward. As you all know, like OSPF and ISIS both have a mechanism to disseminate state in the network. We decided to generalize this idea and use this as a data bus to exchange data between applications. So once you have this, you can basically write any application on top. The other problem we had with solutions which exist at this time was the choice of language. Most of routing protocols written in C, and it's a nice language, no arguments here. Unfortunately, it's really hard to support. It's really hard to extend and really hard to test. If you look at open source implementations, they often lack decent testing frameworks, and this was one of the biggest pain to develop things quicker. As you can imagine, we chose C++ because it's a very common language at Facebook. I mean, I wouldn't argue it's the best language. It's just we use it a lot. It has reasonably high abstraction level, and it was really, I mean, it has lots of libraries inside Facebook and outside, which made it very flexible for our needs. So once we have this, it's straightforward to create applications on top. You have the database system to distribute state. You have the good language. Well, good, it depends if you are like C++ or not. And you can build applications on top of this. Luckily, about the same time, I think this was March, February last year, Telegraph project became discussed at Facebook. So Telegraph folks came to us saying, hey, we want to do some routing. And we're like, hey, we have an idea. Let's try OpenR as a solution for needs. And Telegraph at the time was very different because unlike common networks, it's a complex mesh. It's a lot of hops. And what people wanted is a solution for very fast rerouting and also the option to add extensions quickly in the network. So Telegraph was our chance. And then we started building the actual implementation. So the first component was zero message queue. I'm not sure if you guys heard about this before, but it's a very well-known library outside of Facebook in open source. It offers you a very simple way to pass messages between applications or inside applications. It has a very simple socket API. It's easy to use and has bindings in almost any language. C, C++, Go, Haskell, basically anything. And best part, ZeroMQ was pretty well documented. It was really easy to ramp up and start playing with it. This is an example of a few of ZeroMQ's messaging patterns. As you can see, it's a nice diagram which shows you how you can send messages from one node to another. And particularly, most important for us was the pub/sub pattern, because pub/sub is effectively an essence of any message destination protocol, because you have to send messages to multiple nodes in the network. So next thing was message encoding. If you look at OSPF or SIS, the documents span, well, OSPF at least, hundreds of pages defined in formats of packets, frames, encoding, and so on and so forth. We did not want to spend time defining all these encoding rules. We simply chose Thrift. Thrift is a library that offers you a way to encode data and transport data between applications in an application-agnostic fashion. I mean, it's just one of many. There's also Google protocol buffers. There is, I think, Avro. If you folks remember, was SunRPC in the past, in the 80s and 90s. But Thrift became very popular at Facebook. It's well supported. It has some nice properties, like you can extend the structure, and it still maintains compatibility with the older format. This is an example of how a structure definition looks like in Thrift. Looks like very simple. It's very readable. This one defines an adjacency of routing protocol. As you can see, it has very well-known fields. String is there, integer is there, with complex data types like IP address and so on and so forth. The nice part is once you have this struct, you get the encoding and decoding code for free. So Thrift compiler generates you over parsing code and serialization code. You don't have to worry about this part at all. And so once you combine ZeroMQ and Thrift, we got a very simple, very flexible, and I would say pretty low level, but very powerful message bus. And this was a foundation of all our applications we built for OpenR. This slide gives you like the overview of main components of the system. With two boxes there as the two nodes. Like every node has 4 components. If you ever seen the document describing ISIS protocol, this looks very, very similar, and no surprise because it borrows a lot from ISIS. In fact, I think ISIS was kind of inspiration for all discussions as a nice design protocol in the past. This defines the data flow between these components. Don't have to worry about this right now. We'll discuss all these pieces in more details later. OK, so first piece, the first stuff we built historically was the key value store. So the key value store generalizes the linked state database concept from OSPF or ISIS. It allows you to synchronize and disseminate arbitrary state in the network. And the state in our case, as you can imagine, is key and value. It's very opaque. You just have string of key and string of value. There's no limits on size, by the way. Like OSPF or ISIS have like always frame sizes, fixed formats. In ZMQ, you just have TCP. You can send very large objects if you want. Nice part, it was really easy to implement using ZMQ because most of the mechanics is taken care of by a library. So you only have defined very simple protocol bindings, a few threads, and we just work together. In our case, the value is always a Thrift object, so it has really nice structure. What this means, you can receive an object and parse it immediately into like a C++ class or a Python object or Go structure. And obviously, we used pub and sub sockets very intensively in this model, so we didn't have to worry about the complexities of publications and subscriptions. We definitely had to spend some time to optimize the flooding. Telegraph is planned to have pretty large meshes, like thousands of nodes, and very complex topologies. And so the idea was, hey, can we really handle this many messages in our KV store? Like this diagram shows you a mesh. In OSPF or SIS, flooding is very simple. You send messages, they fly everywhere, they bounce, and they eventually reach every node. In our case, we try to optimize and combine the ideas from different protocols. So first of all, we group the nodes in the network in clusters. So this clustering can be done by configuration or using simple protocol for discovery and cluster formation. But once you have clusters, in every cluster, you can prune the structure, like the successive links, to form spanning tree. So once you have spanning tree, you reduce the number of the links you have to flood data over. So as in packet inside cluster B in this case, you only have to cross this subset of links. So this basically copies the spanning tree idea into control plane. So between clusters, we use the idea that BGP has path tracing. Like if cluster A sends a message, it comes back, it's being blocked because it has the cluster path and its sequence. So basically, we just block messages if you come back to the same cluster again. I mean, there's nothing new here. We just combine the ideas from a spanning tree and a BGP to optimize flooding. So effectively, inside every cluster, you have spanning tree, and between clusters, you have BGP-like loop detection. So scaling was a big topic, obviously. Hey, can we get this link state protocol very, very large, like tens of thousands of nodes? Because common sense says, hey, you can't really do this. Flooding is very limited. OSPF probably can run up to 1,000 nodes. ISS may be about the same. If you look around, there is no research data that shows you the actual scaling limits. People have deployments. They're kept pretty secretive in most cases. So we decided, OK, we have pretty powerful boxes for telegraph. CPUs are pretty beefy. We have even beefier CPUs in data center or in the backbone. So we probably won't run into CPU issues. The problem is that ISIS and OSPF were designed in like 90s, sorry, even 80s actually, when CPU was very, very scarce, memory was very small, and people worried a lot about efficiency. In our case, we found out we can run up to like thousands, tens of thousands of nodes in Telegraph or in our network pretty easily. The other concern people always have with these large topologies is shared fate. Like if some bug hits all processes, it cascades and destroys the whole network. In most cases, all our designs are partitioned. Like data center has 4 partitions, like 4 spine planes. Our designs have similar structure. So you have independent topologies. And if one of them has a problem, it doesn't affect the other one. And you can also deploy the changes, say, per slice or per plane, and limit the impact to only 1/4 of the network. And last one, we built pretty intensive simulation testbed, which allows us to emulate networks of up to like 10,000 nodes in size, I think even bigger in some cases, and then stress test the topology to make sure that every change we make doesn't affect stability and protocol keeps converging and not failing. A few words on client API. So key value store provides a very simple way to receive notifications. So a client simply subscribes to data feed from a publisher. In our case, publisher is KV store. And so effectively, you receive state changes only. And if you want, you can request a full dump or a particular key. Overall, it's a very, very standard key value access API with a simple mechanism to notify of changes. So next part is the hello protocol. If you look at OSPF or SIS, hello protocol is a part of the system. Like in our case, key value store just runs on TCP. It's an independent mesh. This mesh can be built on top of any topology. Hello protocol runs in a separate module. It's probably easier to think of this as something similar to BFD. People know what BFD is. In our case, we simply wrote, I would say, probably 1,000 lines of code to implement this protocol. It sends thrift structures and USB packets, and it serves the purpose of detecting neighbors, measuring, say, link latencies, and doing other things which pertain only to one link. As I mentioned, it doesn't have much logic. Its open source main purpose, discover neighbors, and then communicate this information to the rest of the system. But nice part, we can develop this component separately, test it separately. It doesn't tie in any way in the key value store. And overall, this modularity was key principle to design the system. We can replace any module very, very simply because all we do is talk to each other using ZMQ. This example just shows you the structure of Hello packets. It has Spark in the name. So Spark is how we call this protocol internally. In this case, as you can see, it has extremely simple payload with node name, interface name, and transport addresses. So the transport addresses are used to tell the key value store how to connect to our neighbors. Security-wise, luckily for us, well, actually it was partially choice. ZeroMQ has already implementation of elliptic curve security. It actually copies the curve CP protocol implementation. So you basically get security for free. Once you have public keys produced for every node, you can encrypt and authenticate every session. So effectively, simply by using ZMQ, we just get the security for every session for all the data we send and receive. And the public keys, in our case, are being transported in Hello packets. So the moment you detect a neighbor, you have a public key, and you can start a handshake. Of course, authentication has to be done separately. Like you have to validate the public keys using different mechanism. All right, so link monitor. Link monitor is the component that is responsible for discovering interfaces in the system. It scans interfaces. In our case, it uses Netlink to discover interfaces. Luckily, it works on most platforms we actually support. It allows you, once you discover interfaces and neighbors, to communicate to key value store and tell it, hey, I have a neighbor, please form a session to this guy. So effectively, you can think of this as a kind of BGP without discovery. Or the other analogy could be LDP, which discovers neighbors dynamically and then forms the sessions. The other, I would say, very important aspect, link monitor communicates to the FIB module, which talks to forwarding plane, and informs it of the link events immediately, which allows us to detect and reroute very quickly. So basically, when a change happens, you inform the FIB module instantly, hey, there's a problem, remove this path from use. And this was primarily for Telegraph, because Telegraph wanted to recover from link failures very, very quickly. OK, so decision module, it's pretty standard, I would say. You heard about this before. What it does, this guy subscribes to key value store. It receives the adjacencies and prefixes. It computes the shortest path tree and produces the routing tables. It then pushes them down to forwarding module and says, OK, program this into the forwarding engine. So effectively, this is very similar to what we have in ISIS, logically, except that we didn't have to write SPF ourselves because the libraries, they do this already. I would say decision module is one of the simplest. It has very basic logic, get data, SPF, and publish the state. These two examples are tree structures. This is what decision module uses to implement the computations. It's, I would say, just 6 structures, right? And the nice part, we describe them separately in a thrift file, which defines you the structures. It then generates all the code for you automatically. Like, you get the C++ code out of this like, for free, basically. In this case, you have very standard like, pack of the data that any link state protocol would use. So another idea, I would say this was new. ECMP is a very common data center. So equals multipath is pretty common. Telegraph needed something to provide path protection. And in many cases, in mesh networks, you don't have this ECMP property. Because of meshiness, you have lots of loop-free alternatives. So this was the stuff which wasn't like readily available. I mean, this is the well-known idea. There are implementations. It just wasn't available, and things we've been actually trying to use before. But the idea is you can use the loop-free alternates easily. It was just a simple tweak to SPF. And once again, this change was probably very minimal. I would say it probably took us maybe 10 lines of code to implement this. And if you had to ask a vendor to support this on a given platform, it would probably take you a few months to get the feature. In our case, we use loop-free multipath in two variations. One variation is, can we use all the paths together and load balance traffic? And the other one, hey, can we use this as primary and backup paths? OK, the last guy, I think it's the last guy, feed module. So one specific about this guy, it's the only component that has dependency on low-level details. So this guy has to talk to the low-level SDK, say Broadcom SDK, or the stuff we had in Telegraph, which was different SDK, or any other platform. They all have their own SDKs to talk to the platform. It receives the full snapshot of the routing table. It keeps the state, it puts the deltas, and then pushes them down to forward database. And as I mentioned before, this guy also gets the feedback from the link monitor. So when the link goes down, it can remove the backup paths, remove the affected paths and activate backup ones. Overall, that's the only piece that depends on low-level details. And this is how it works. We have two pieces. First one is a FIB agent, C++, platform independent. This guy talks over RPC to a simple service, which implements Thrift API, Thrift server. And this guy, in turn, links against the low-level library. And every platform has its own library. But luckily, it could be any, it could be 32-bit, 64-bit, or anything. Thrift service kind of hides this from you. So for different platforms, we have different APIs. There is nothing, I would say, too fancy. It just was very simple to write it this way. Let's say for Linux, for testbed, we use Netlink API to program the FIB. All right, a few other things. I mean, any protocol needs this stuff to operate safely because we have to roll the changes very frequently, maybe like daily or weekly sometimes. It depends on the cadence. We had to implement graceful restart. If you look at OSPF, graceful restart RFC, it's pretty complicated. Well, not very, but reasonably complicated. We did something simpler, slightly more hacky, but it works really well in our environments and allows us to restart image anytime and maintain the forwarding at the same time. Drain and drain, Facebook is, I would say, philosophy is maintain high reliability. So we're very sensitive to having tools that allow us to move traffic on and off of the device for maintenance purposes. In most cases, it's not necessary because graceful restart allows you to keep traffic, but just in case it was an important feature. And CLI-wise, we just built a Python script. I would say it probably has 5 commands. The nice part about link state, you don't have to worry which node you query. Like all of them have the same state. So once you have these audits which check, OK, every node is synchronized, you can query every node and get the same state, same database. So debugging-wise, it gets, I would say, even easier in BGP because state is the same everywhere. IPv6 was a big story for us. We use IPv6 for communications. It was very simple. We don't configure any address in any link. It's all link local. So in this sense, OpenR is basically pure autonomous. It bootstraps, it discovers neighbors, and you don't have to set up anything on any link. Like in Telegraph, you bring the devices, bring up the links, they just work. You find the neighbors, form adjacencies, authenticate it, and it works just fine. And this is one of the ideas we had behind OpenR, is being autonomous in the network, so we can eliminate the amount of work we have to put in configuration. I mean, this idea is kind of arguable. People keep saying, hey, we need more control. But we try to balance. We try to offload this configuration. We don't need stuff like addressing. And with IPv6 was basically trivial. You already have all this stuff for you automatically. Of course, we had supported before because we still have it for traffic. But it's very simple. You assume topology is the same, and you don't even need the 4 next hops. You can use the 6 next hops to program forwarding state. So the first implementation was for Telegraph, as I mentioned. I think you heard about this from George earlier this morning, so I won't tell you too much. the initial requirement was, hey, we start it quickly, and we want this to converge fast. And then, okay, can we extend this more and more later on? Okay, fine. And also the requirement was, we want this system to communicate to the central controller to get data and push data, like topology information, link bandwidth, and all other things. So in a sense, OpenR was also a system to provide information to central controller. Specifically, just for Telegraph, we had to do a few things which aren't very common in like networks. First one was the address allocation. Like address allocation is normally done using DHCP. In our case, we just built a system that uses KV store to basically auto-allocate addressing. It's called the Adhoc Addressing. It was a big research area, like maybe 12, 15 years ago. Hey, address allocation in mobile networks. I think it was very simple. Once you have this broadcast KV store, you can easily partition the address space and sub-allocate addresses without any central authority. Next one was bandwidth allocation. So this one's more tricky. Let me pull back a little bit. First of all, Telegraph is a mesh network. And the trick is folks who are closer to the internet, to the sink, they get more bandwidth because they're closer to the source, and so we pull more traffic. It's pretty problematic in big mesh networks, so you have to implement some sort of fairness logic and shape people who are closer to the internet and give them less capacity, just to equalize all the members of a network. In our case, OpenR computes these weights using just topology information, and this provides you with backup in case if there is no controller to tell you these weights centrally. So in many ways, OpenR is basically a backup system to provide you coverage when central controller is gone. Okay, next things. We do have applications for OpenR in our areas of a network, in parts of backbone and data center. This is where it integrates perfectly with some of the control systems. That's all to talk about, so I probably won't cover it here. But just for information, we have other use cases outside of Telegraph, and we are looking to make this our uniform application for multiple networks. Open source is always a common question. It's definitely in scope. Right now, the amount of work is still pretty active, so we'll probably open source this, but at some point in the future. Okay, last few words. I'm almost out of time, but it's perfect. Few key insights for us was, it was extremely helpful to be able to own our own fate. Once you control the code, you can move at your own pace. And you can do whatever you want. It may not be actually useful immediately, but it gives you this benefit of being able to change things when you want this to change. You don't have to wait for somebody outside to do this for you. We pivoted from building protocols to just a platform, and routing became just one function on top of this. And last but not least, we found out that combining this autonomous function and centralized function was the biggest win, because some things are much better to be done in the network, while some things work much better in centralized controller. And I think that's it for me. Thanks for listening. If you have any questions, feel free to ask me. Jeff?
You didn't talk about, great talk. You didn't talk about the metric assignment. Since you are computing LFAs, are you pre-assigned some metrics, or you're trying to optimize, which makes your program hard afterwards?
I see. So I think I skipped that part. The Hello protocol also serves to measure the round-trip latencies. For now, it's kind of autometric, which we use. We use latency to discover metrics. Of course, there's basically some base metric we assign initially. But right now, we try to experiment with this autometric, which is RTT. In data center, and the backbone is always static. It's like basically fixed based on latency. But yeah, I think I skipped this part.
In your topology, you'll get around 83 to 89% coverage with LFA.
Right.
What do you do with uncovered links?
So I think we did analysis for Telegraph deployments. The coverage was about 90-something. It was actually pretty impressive because mesh was very uniform. It was 97%. It was much better than I expected. I was thinking maybe like 60%. but it was like 90-something% coverage in models.
Do you plan to support post-optimization to make coverage close to 100%?
I'm sorry?
Post-metric optimization, so after figuring out there's no coverage for LFA, you might change metric and...
Oh, no, we didn't do this. For now, we just we try to still, we're very incremental. Once this kind of been fully vetted and tested, in production, we can move forward with metric changes. I think this becomes an interesting aspect of trying to adjust metrics to get full coverage, but not there yet.
Thank you.
Thanks.
How do you define your cluster boundaries? Like, if there are more nodes, would it scale well? I know it's a immutable.
I see. Yeah, it's a good question. So basically, think of this. Initial setup was just static. Okay, you configure this by hand, like in configuration. But then the idea was, what we have, you have beacons, like some nodes, like in span tree, you send the hello packets, you propagate data, and they decrement the count. And effectively, you build a spanning tree from a root node, and it becomes like a center of a cluster. So effectively, you have multiple. So think about this. In spanning tree, if you have multiple roots, and you have a threshold on the time to leave, you effectively form multiple trees. The same logic here. You have some nodes which become the sources of a spanning tree. They send their hello packets, and you decrement the hop count. And then this forms the cluster boundaries. So everyone who hears from this guy with highest priority will be on his cluster. So this was kind of one of the ideas for cluster out discovery. Right now it's experimental. For production, we use this manual assignments because it's kind of more practical. But we try to get to the state when we can have a fully automated cluster allocations.
And one more question. How do you break the loops in the cluster? Like...
Nothing fancy, just span tree, right? You build a span tree, use span tree protocol. You compute the span tree, okay, I should only flood this direction towards the root. So as opposed to span tree, which computes the tree in data plane, it builds the tree in control plane. It tells you, okay, only send over these links.
Maybe one more question.
Oh.
Whichever. You talked about multicast, multipath, and you talk about the only metric you're using is latency. How do you cope with trying to load balance across, say, 3 10-gig links over here and a 100-gig link there?
So in this case, the idea, more complex logic is done in controller. So basically, this provides only simple, fast recovery. So loop-free alternates, loop-free multipath was a nice feature. You can load balance. It doesn't meet any centralized constraints. As I mentioned, we have the central controller, which talks to this system. So this guy has a full view. It has traffic matrix. It can compute the optimal distribution of flows. But this full loop-free multipath was mostly for protection. We did experiment multipath. It's nice, but it's primarily for path protection, local restoration. Any more questions? Other time. Okay, thank you.
Thank you.
Thanks, guys.